Okay, welcome back to the next part. We need to finish the methods for these are the undistorters. So let me quickly fix that by writing undistort. Undistort. We have written quite a lot of code in the last time. And we are still not finished. This is because the photometric undistorter and the geometric undistorters are quite complex. They have a lot of maths and we need to do several things. Okay, let me quickly finish up this one. Those are not distorters, but they are undistorters. Okay, hopefully this will not take a lot of time. So let us continue with the undistorter. So last time we have found out that the makeOptimalKFull method is simply an assert false, so it is not defined. If it is called, the program will finish with a false assertion, and therefore this will probably not get called at all. Okay, but now we need the undistort method read from file. So let's create that. It is a void and it's in the undistort. And then there's a read from file. And this method takes in a const char pointer to the config file name, like this, and a number of parameters, int and parse, and a standard string for the prefix. Okay, and inside this read from file, we will read the file. Which file do we read here? We read the camera.txt file. This is our config file when we look at the argument list. So first of all, we need to initialize some variables. We have a photometric undist variable, which is our photometric undistorter. This one is 0 in the beginning. Also, it is not valid. So valid is false, and pass-through is also false. We assume that we, well, in this case, not just pass through, but actually process the file. And we also have a remap x, which is 0, and a remap y, which is also 0. Next we have a new float array called output calibration, and it has 5 elements. And we also set the parse arg, so the original parsed arguments, to a new vec of dimension x, and initialize it with nparse. So we basically create a new vector. If nparse is 5, we create a 5D vector. Next, we read the parameters and we create an input file stream, which we call infile, and we pass the string, which is config file name. We read the parameters, by the way, from camera.txt. The first thing we do after we have opened the file, we assert if inFile is good. Next, we create a standard string, not only one, but 4 of them, each for the 4 lines that we have in this camera.txt file. So L1, L2, L3, and L4. Create strings for each of the 4 lines. Next, we simply read all of the lines. So we say standard get line from the inFile and put it in L1. And we do the same for each of the lines. Like this. And simple as that. So in the L1 to L4 variables, we now have the contents of the lines. So the first line is contains the camera parameters. The second one contains the original image resolution. Then we have either crop, full, or parameters. And then we have the resulting image resolution. Okay, for line 1 and line 2, we do the following. First, we check if the number of parameters is equal to 5. Then we have the FOV model. So we need to handle that now. First, we create a new char buff variable, which can hold 1000 characters. So this is our buffer. Then we call the snprintf function, which puts text into the buffer with the size of 1000 and with this string format. So we expect a $s and then a $LF, which will read in a float number for us. And we'll repeat that 5 times or 4 times, so that we in total have a string object here and 5 float objects following, or float entries, we could say. And next we say we put the prefix, so the $s, into this prefix variable, but we pass the C string. So the prefix, to recall that, can contain either pinhole or FOV or equidistant or Kanalabrand. This prefix contains the camera model, or can contain the camera model, but does not have to contain it. It's not mandatory. Next we check for if standard scanf. We check L1 and the C string of that. We put it in the buffer. So we read from L1, put it in the buffer, and we want to use this. We want to put the content into the variables for parse_org. And we start with the first index and then add the other ones here. So 0, 1, 2, 3, 4, 5 in total. And the result from scanf should be 5. So this is our first condition, but we have another one, which is we also want to standard scanf, scanf, line 2, and here the C string again, in the format of %d, and once again %d, to contain our, as I have written here, the original image resolution. That is, for the first parameter we have WORG, and for the second parameter we have HORG. So the original width and height, and the number of red values should be 2, should be equal to 2. So these are our conditions we want to have met. So we have in the first line we have 5 parameters, in the second line we have 2 parameters, and if this is successful, then we do something. Namely, we want to print the parameters. So we write standard cout, and we say input resolution is in this case WORG, and HORG divided by a space, or separated by a space, I mean, and then we make an end line. We also print a new line which tells us that the parameters that go in are as follows: parse_org 0, and next we have all the other parameters. So we have 0, 1, 2, 3, and 4. And after that we have simply a new line. And this is it for the first condition, or for the true statement. And else we want to print out that we have failed to read the camera calibration, with the question invalid format. Then we add a new line and also print out the calibration file, which is in our case the config file name. And then we end the line. We will in this case also close the in file, because we are now returning from this function and we do not want to leave files open. We always want to close them and then we return. Okay, so this is this part if we have 5 parameters. And this is, by the way, not only the FOV model, but I will also add the pinhole model, because the pinhole camera model also can contain 5 parameters. Okay, next we will have the case where nparse is equal to 8. So we add an else block, more specifically an else if block. We say nparse is equal to 8, and this will be useful for the KB, so Kanala-Brunt, equidistant, and Rattan camera model. And the content will be quite similar to the part where we read in the 5 parameters. So let's copy it here. And let us adjust. So we have this still the same buffer with 1000 characters. But this time we will have still the string here, string placeholder, and the float placeholder. But those placeholders for the floats, there can be 8 now. So we have 5 at the moment. And there are actually 10, I think, in the original code, which is weird. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, there's really 10 of them. So let's just add the 5 more. So this should be 10 floats now. And we still have the prefix C string here, just as before. Next we check for if standard sscan L1 C string and buffer. We simply take here not only 5 original parsed arguments, but we will now have 3 more of them. So even though our format here above contains 10 elements, we are just taking 8 of them. So after the first 5, we have here 5, 6, and 7. And this is obviously not equal to 5, but obviously equal to 8. And next we also have line 2, which is not changed. So we also have in line 2, in this case, the original width and the original height, which are 2 parameters, and therefore this is fine. Okay, if this is true, then we print out the input resolution with w.org and h.org. And we say, or we print all of the parsed arguments, which is in this case also the prefix string. So in goes not only the parse org, but also this prefix .c string. And then we have let me quickly check that here. Okay, I was missing a space here. Let's put it in there. So we print out the prefix, and then we print out the parsed arguments at position 0, 1, 2, 3, 4. But now we have 3 more. 1, 2, 3. So we have a 5th, 6th, and 7th argument here. Let's make this more beautiful. Like this maybe. Okay, so this is the part when the scanf command returns true or evaluates to true, and this happens if it evaluates to false. Here we keep the statement failed to read camera calibration invalid format, and we print out the calibration file, which is the config file name, and we close the in file and return. In case our number of parameters is not 5 and not 8, what do? We just say that there is an error. Namely, we call standard cout with called with invalid number of parameters for dots, and then forgot to implement me. That's a really harsh question. Standard end line. And once again, we take the int file and close it, and we return. Okay, here we have read in the parameters for each line. Well, we only have line 1 and 2 here, but we want to do something with the values, so we need to do that now. So here we do not apply, but we update the parsed parameters based on the image dimension. What does that mean? You first check if the parse org the parsed argument at position 2 is less than 1. And if parse org at position 3, so the 4th argument or value, if this is also equal to, or if this is also less than 1, I mean, then we do the following. We print something, standard cout, standard end line. We're actually first adding some end lines, 2 of them, and then we say found fx is equal to what? To parse org at position 0. And next we also print the fy, so comma fy is equal to parse org at position 1. And we continue with the principal point, so cx and cy, which are at position 2 and 3. Yeah, let's add this end line here. But we also want to print I'm assuming this is the with escape sequence relative calibration file format, and will rescale this by image width or height and will rescale this by image width or height to fx is equal to, that we have parse org at position 0 times w org. So we take fx or the relative fx and multiply it with the original width of the image. And then we add the other ones, like fy is equal to put this in a new line. So fx is here, fy is parse org at position 1 times the height, the original height. Then we have cx and cy, which is then parse org at position 2 times w org, and cy is parse org 3 times the original height, but not exactly. We also need to subtract 0.5 from that. From both of them. Which is kind of weird to me, because it should be the, it should rather be w org times 0.5, and this should be subtracted from parse org times w org, I think. So I think there is an error here. But maybe I'm mistaken, so let's keep it like that. It works after all. And this is where it ends. Let's keep this in one line. So after that, after cx and cy, we add an end line. Can also add a full stop here and 2 end lines like this. It's a bit of a mess, but I think it's still readable. Okay, what will we do here? Here we will rescale and subtract 0.5 offset. Let's keep it like that. Subtract an offset of 0.5. Well, we can say rescale and subtract, or offset 0.5, maybe like this. Then we have the 0.5 is because I'm assuming the calibration is given such that the pixel at 0,0 contains the integral over intensity over 0,0 to 1,1, whereas I assume the pixel 0,0 to contain a sample of the intensity at 0,0, which is best approximated by the integral over negative 0.5, negative 0.5 to 0.5, 0.5. Thus, the shift by minus 0.5. Well, I don't know about you, but I do not understand this comment. Why is there an integral over intensity here if we are talking about pixel space, which usually only has geometric meaning and not the photometric meaning? So yeah, I'm not sure what this means, but what we have to do is we have to set or update the parse org at position 0 with parse org at position 0 scaled or multiplied by the width, the original width. This makes sense so far. Of course, we take the relative value here and multiply it by the width to get the absolute value. This makes perfect sense. We do the same for the fy value, so the focal length in y, but this one will be multiplied by the height. And we also do the same with the other ones, so cx and cy in this case. We take the old value, multiply it with height, with width and height, but here we subtract 0.5. which is something I do not understand. Just doesn't seem correct to me. So I will write a to-do for me. Why or what does that has to do with intensities? I need to find it out at some point, and maybe not if the algorithm is working, but if the algorithm is not working, I would have to check that. Okay, next we continue with line 3. And line 3 can be of, can contain 3 kinds of content. So if L3 is equal to crop, then we want to set the output calibration parameter 0 to -1, and we want to print out standard cout out rectify crop and then standard end line. Next, we check with an else if line 3 contains full. Then we set the output calibration at position 0 to -2, and we print out rectify full, like this. And the third case is that else if L3 is equal to, okay, there's also a case none. In this case, we set the output calibration at position 0 to -3. And we say out no rectification. And then there's another case if L3 has a different definition. Let's quickly look up this in the dataset. So here we have sequence 45, camera text. Here, this third line is crop. And in the sequence 2, the third line contains these magical numbers here, which we need to handle now. So here we say that else if standard scanf line 3 C string, if this is in the format %f 5 times 3, 4, 5, then we put it into our output calibration. So output calibration at position 0, the reference to this, 3, 4, 5. Let's put this in a new line. So this is output calibration 0. Then we have 1, 2, 3, 4. And this should be equal to 5 because we have 5 parameters. Okay, so if this is true, then we print out again the word out, but then we add all of those parameters. So we have this output calibration 0. Then we add a space and we continue with the other ones. Like this one. Maybe not that ugly. Here is 0, then is 1, 2, 3, 4. And after that we want an end line. Like this. And then there is one else block still left to code. Else. And here we want to print out cout. Print out again, and now failed to read output parse, not rectifying. Not rectifying. And we add a standard end line. And we need to close the in file and return. So this is about line 3, which can contain crop, full, none, and 5 output calibration parameters. Maybe not and, but or. And we need to check them here. We did that. So next is line 4. What can this line contain? This will contain, as we have written above, this will contain our output resolution. So we first go ahead and check if standard scanf, line 4, C string, we expect the format %d, so 2 integers, which should contain our final values of width and height, and the function should return a 2 because 2 arguments or 2 values have been parsed. And after this returns true, we check if we have a benchmark setting on. Benchmark setting width is not equal to 0. Then we say W is equal to benchmark setting width, and if the output calibration at position 0 is equal to -3, Then we want to override this output calibration at position 0 with the value -1, which means we want to crop instead of none, since probably resolution changed. And we do the same with the height. So we copy that part and say benchmark setting height is not equal to 0. Then we set h is equal to benchmark setting width. No, it's of course height. Benchmark setting height. And here we say that once again, if the output calibration at position 0 is -3, then we want to override that with a -1, and that means we want to crop instead of none, since probably the resolution changed. After checking the benchmark setting, we want to print to the screen that the output resolution is W and H. And we end the line. I will add an X here to communicate the times. And next we will have the else part, in which we will print not the output resolution but out, and then fails to read output resolution not rectifying. And then we end the line, and this is it for line 3. But now we want to do some magic to calculate the final calibration matrix. For that, first we need to initialize the remap x array to a new float of size width times height. We do the same with the y value. Remap y, the same size, and then we check if output calibration at position 0, if this is equal to -1, then we have, let's quickly look that up. So we want to crop here. This means we want to crop the -1. So we need to call make optimal k crop. Else if the condition is output calibration at position 0, if this is equal to -3 or -2, I mean, then we will call make optimal k full, which gives us an assertion error. So this is probably not going to be called. But then we have the else if statement output calibration at position 0 is equal to -3. And here we need to check for the width and height. So if w is not equal to w_org, or height is not equal to original height h_org, Then we want to print out to the console standard cout. Want to print out an error, rectification, mode none, requires input and output dimensions. Okay, that's probably dimensions. Dimensions to match standard endline, and then we exit with the code 1 or the status 1. If we do not exit, then we set the K matrix to the identity and we fill up the values of the K matrix. So first of all, the top left 0 0 to be parse orc at position 0. Next we have 1 1. So the center of the 3x3 matrix, this will get the parsed parameter at position 1. Then we have 0 2 and 1 2. The fifth one can be deleted. This will get the parameter at position 2 and this one at position 3. And then we set pass through to true. So if we have an error, we do not want to, let me quickly check, what do we want to not do? If not pass through, it's in the undistort method. Not pass through, then we simply want to copy the photometric undist output image into the result image. So we do not want to touch the image at all. We are already at line 1100. So this is a very long file, but not as long as the other ones that we will write in the future. So this one is pass through is equal to true. And then we have an else block. And we check if output calibration at position 2 is greater than 1, or output calibration at position 3 is greater than 1. Then we want to print something, standard cout. Warning, given output calibration in this parentheses seems wrong. It needs to be relative to image width or height. Exclamation mark. And we will add three end lines. And in the beginning, we will also add 3 end lines. So here we want to print something. That is the output calibration at position 0. And there are 4 parameters we want to print. So 0, 1, 2, and 3, and we'll put that in a new line. Like this. Maybe let's break here as well. So this output calibration seems wrong. You can remove this space. And we will move this end lines to a new line. So what does this mean? We have an output calibration. We have the 3rd and the 4th parameter, which are greater than 1. And these should mean the CX and CY. Let me quickly double check. Where are they set? Here. So the 0, 1, 2, and 3. Yes, these should, as far as I understand, they should check the CX and CY parts to be less than or equal to 1. Zero, 1, 2, 3 should be fine. Okay. Okay, even though there is a warning, this will not lead to the program exiting or crashing or something. We'll just continue at this point to set the K matrix to identity and to still set the calibration parameters as we did here. So I will just copy that. We set them not to the parse org, but to the output calibration. But multiplied by width and height and width and height. But these ones here, the CX and CY, will be subtracted by 0.5. After finishing this else block, we want to add an if block. If benchmark setting fx, fy, and fec is not equal to 0, then we want to use it by setting the calibration matrix at position 0, 0, so the top left of that, to fmax of benchmark setting fx, fy, and fac and float of k at position 0, 0. And we also take the max to set the position 1, 1 by comparing it with the old position k1, 1. And after that we set pass through to false, because we cannot pass through when fx or fy have been overwritten. Like this. What we want to do next is we have this the remap x and remap y arrays prepared. Now we need to fill them with values. So we have a for loop which starts with the y values. Y is equal to 0, then y is less than height and y plus plus. And then we have a nested for loop for the x values. X is equal to 0, x is less than width and x plus plus. And here inside of those nested loops we say remap x at position x plus y times w is equal to x, and remap y is the same, x plus y times w is equal to y. So here we fill the remap x, y arrays with ascending numbers. From 0 to width or height. Okay. Next we want to call the distort coordinates. Remap x, remap y, remap x, remap y, and height times width. Next we will once again have this nested loop. We start with y, y is less than h, y plus plus. And the next loop is x equals 0, x is less than w, x plus plus as usual. And here we want to make the rounding resistant. So we create two floats. Float ix is equal to remap x with the position x plus y times w. And we also define an iy is equal to remap y at the same position, x plus y times w. Then we need to check if ix is equal to 0. Then we want to set ix equal to 0.001. And if iy is equal to 0, then we want to set iy equal to 0.001. But if ix is equal to work minus 1, then we want to set ix is equal to work minus 1.001. And we do the same for ixy, horc minus 1, ix is equal to horc minus 1.001. Okay, this is weird. I would expect ix to be iy, just as it was here. So this seems like a bug to me. So I will add a to-do. To-do, check if there is a typo. Ix should be iy. Okay. What we do after that is we check if ix is greater than 0 and iy is greater than 0 and ix is less than worc minus 1 and iy is less than worc negative 1. Once again, this seems like an error to me, to be honest. I would again assume that this should be not iy less than worc minus 1, but it should be iy less than horc minus 1. I would need to check that as well. But currently I'm trusting the code base, so let's continue like that. And here we want to remap to set the remap values for remap x and y at position x plus y times w is equal to ix and iy. And in the else case, we want to set them not to ix and iy, but to -1. Like this. Okay, after the two for loops, we say valid is equal to true. And we can print our rectified camera matrix. So standard cout, rectified camera matrix. I would change this to rectified camera with a C matrix. And we'll also add the end line in the beginning. And in this case, we can just print out the matrix K. Maybe let's add an end line here and 2 end lines here. Like this. Okay. So the whole purpose of having this huge lines of code here is to read the camera.txt file, parse this file, get the parameters, and calculate a new camera calibration matrix K, which is rectified. I'm not sure if this word rectified means the same as in stereo, where we have the images, and if we have a stereo setup where the cameras are not parallel but are in a converging configuration, for example, then we take the images and make them planar, sort of planar. I think rectified means in this case that we want to correct the camera matrix. So we have probably in this line a few correction terms, which are then simply applied to the camera calibration matrix that is defined here, which will in turn deliver this output resolution. But I'm honest and I say I'm not really sure about the details that have been implemented here. It still seems to me like, yeah, complex code where I really would need to step through using a debugger, and where I need to try to understand what exactly is going to happen at each time step. But for now, let's take it as implemented correctly, and let's not question it at the moment, because currently we just want, in this video series, we just want to go through every part of the LDSO and try to understand it, at least so far that we are able to change specific parts. So if we want to simply assume that the camera calibration that is given here is perfect, then we can as well simply get rid of all the code here and just set the camera calibration matrix K as being the correct one. Okay, let's continue with the undistorters for the individual camera models. So for the constructor, we define undistort, then FOV, because we are now implementing the constructor of the field of view camera model, undistort FOV. This one takes in a const char pointer to config file name and a bool with no prefix. And here we want to print that we are creating FOV undistorter. standard end line. Next, we want to check if no prefix. Then we want to read from file. We pass it the config file name and a 5 for the number of parameters, but nothing for the standard string prefix. And else, we also want to read from file. We pass the config file name, 5 as number of parameters, and this time an FOV as the prefix. And I think it's probably important to add the space here. So that it is removed from the parsing step. Okay, so this is the constructor for the undistort field of view, which is now very simple because all of the logic is in this read from file method already implemented. Next we have the destructor, which is undistort FOV, and then undistort FOV. And this is empty. And then we have the distort coordinates method, which will start with void. It will return void. Then we have undistort FOV. And here we have distort coordinates. This method will take in a float pointer to in x, float pointer in y, and float pointer out x, and float pointer out y, and an integer with n. It will be a const method, and the body will be defined as follows. This is where all the magic will happen. So let's turn on the music again. So here in distort coordinates, we want to create a float. Dist is equal to parse org at position 4. And now we will create a float. D2T is equal to 2.0f times 10f with dist over 2 times or over 2. Then we have the current camera parameters. So it's a float fx is equal to parse org at position 0. And the same is true for the other 3 parameters, fy, cx, and cy, which are 1, 2, and 3. Then we have the individual parameters from the camera calibration matrix, the current camera calibration matrix. So we set up a float, ofx is equal to k at position 0, 0. And we have an ofy, ocx, and ocy, which is then 1, 1. 0, 2, and 1, 2. Next, what we want to do is we want to calculate the out values. So we have our current camera parameters, and we'll have our camera calibration matrix, which also both reassemble the whole, the complete pinhole camera model. And we want to calculate or compute the out x and out y, and this will be done in this for loop. We loop through with the int I equals 0, I is less than n, and I plus plus. So this n parameter is given to us. Which are the number of pixels we want to undistort, I think. So it's maybe a bit confusing that this method is called distort coordinates. Distortion and undistortion are basically inverse to each other. So even though this method is called distort, we can still undistort coordinates using that. And this will be done here. So in this for loop, we define a float x, which is equal to the in x at position I. Then we have a float y, which is in y. And then we have a float ix and iy, which will be defined using x minus ocx divided by ofx. And similarly, we have y minus ocy divided by ofy. Then we have a float r, which is equal to the square root as a float version of ix times ix plus iy times iy, so the Pythagorean theorem. Then we have a float fac is equal to r is equal to 0, or dist is equal to 0. We check that. If this is true, we set the factor to 1. Otherwise, we set it to a10f of r times dt d2t divided by the distance times r. With this computed, we can now set ix equal to fx times fac times ix plus cx. And we can set iy is equal to fy times fac times iy plus cy. And now finally we can set the out x values at position I, in this case is equal to ix, and we have out y at position I is equal to iy. And this is this method for distorting the coordinates or undistorting the coordinates given some in position and putting them into the out position for n points. This is the whole whole logic to do that using this specific FOV camera model. Okay. Next we want to implement the radton model. So let's copy this constructor here. And let's put it here. And let's change this to, of course we also need to change this, radton. The rest is almost the same. We have this console output creating radton undistorter. Then we check if we have no prefix. If this is the case, we call read from file. But for radton we have not 5 but 8 parameters. Same here. And the prefix is radton that this file could have. Okay, about the destructor, this will also be empty. So let's change that. And this is finished. And now we copy the distort coordinates as well. And let us see if there is something different here. Of course, we want to have undistort radton. Then distort coordinates is the same. We have this in x, in y, out x, out y, and a constant method. But here we have the radton model. This is as used in OpenCV. So therefore, we need to introduce more parameters here. We have 8 parameters in total. So what is missing is not only the pinhole camera model, but also the distortion model, which is usually expressed with K1, K2, R1, and R2, where R is the radial distortion and K is the tangential distortion, as far as I can remember at the moment. Then we have here 4, 5, 6, and 7. We still set up the OFX and OCX and so on and so forth with the camera calibration matrix K. And now we begin to loop through all of those points that we want to distort or undistort. And that is, we first store the X and Y values again from the in array. Then we create new helper variables. mx2u is equal to ix times ix. Oh, and this is missing. Okay. I need to move that a bit further down. So ix is the same still as before. Then we have mx2u, which is ix times ix. Then we have my2u, which is iy times iy. And then we have mxyu, which is ix times iy. So this is basically x squared, y squared, and xy. Then we have a float which is called row to u is equal to mx to u plus my to u. Then we have a float rad_dist u is equal to k1 times row to u plus k2 times row to u times row to u. After that we have a float xdist is equal to ix plus ix times rad_dist u plus 2 times r1 times mx y u plus r2 times row 2u plus 2 times mx2u. And similarly with the ydist we have iy plus iy times rad_dist u plus 2 times r2, okay, r2 times mxyu plus r1 times row 2u plus 2 times mx, no, it's actually my to u here in this case for the ydist, but the rest is the same. So only the r1 and r2 are switched, and this mx is a my here. Then we have a float for ox, which is equal to fx times xdist plus cx. And we have a float oy is equal to fy times ydist plus cy. And then we set the out x and y to ox and oy. And this is it for the field of view, rad10 model. Next we copy the rad10 constructor and put it here. And we take the undistort equidistant, put it here, and we say we want to we are creating the equidistant undistorter, which has 8 parameters as well, but the prefix is now equidistant. The destructor will also copy that and change it to the undistort equidistant. And now we will also copy the distort coordinates from the rad10 undistorter. Oh, let's copy the whole method. Let's paste it here. Okay, now let's check what we need to change. So the argument list is the same. It is also const. But here we are using the equidistant distortion model. It will have fx, fy, cx, cy, and then k1, k2, but also k3 and k4. Eight parameters as well, and we then store the camera calibration that we have in this OFX variables. Then we have this for loop, which starts at I equals 0, I is less than n, I plus plus. Then we store x and y from the in x and in y arrays. And then we have our model. Equidistant model, which starts with the ix and iy values, which are the same. But then we have a float r is equal to square root of ix times ix plus iy times iy. So this is again the Pythagorean theorem. Then we have a float theta is equal to atan of r. Then we have a float theta 2 is equal to theta times theta. Then we have several other thetas. Theta 4, 6, and 8, and a theta d. The theta 4 is theta 2 times theta 2. Then theta 6 is theta 4 times theta 2. Theta 8 is equal to theta 4 times theta 4. And theta d is theta times, here comes the magic, 1 plus k1 times theta 2 plus k2 times theta 4 plus k3 times theta 6 plus k4 times theta 8. Then we have a float scaling, which is equal to r is greater than 1e minus 8. So if r is greater than almost 0, then we, if this is true, then scaling is equal to theta d over r, else scaling is 1.0. Then we calculate the OX and OY values, which are fx times ix times scaling plus cx and for OY it's iy times scaling plus cy. And the out values x and y are ox and oy again. Okay, now we are getting to the Undistort Canala Brandt camera model. So once again we copy the constructor from above. So this is Undistort.kb, Undistort.kb, const char file name, no prefix. Here we are creating the Canala Brunt undistorter. Then we check if no prefix, then we read from file 8 parameters. And if we have a prefix, then we want to read Canala Brunt, also with 8 parameters. And this is it for the constructor. Then we need the destructor. Undistort.kb. This one is empty as well. And then we need the method to undistort the parameters. Okay, here we have once again the Undistort.kb class, which has a distort coordinates method, which takes in values and creates out values with int n and a constant method. And here we have not the equidistant but the Canala Brunt distortion model. Is it with 2n? Yes, 2n. Okay, Canala Brunt. We have here still floats, but this time we have const floats. And also for the O values, for the original values, we still have fx, fy, cx, cy, and now we have k0, k1, k2, and k3 in this order. And then, interestingly, this is quite similar. So once again, we have we loop over the n pixels that we have got, and we store the x and y value from the in pixel here. Then we have not the equidistant model, but we have what is written in the original code as the red tan model again. But it is not the red tan model. A10-2F. No, it's definitely not the red tan model. So let us rename that to the Canala Brunt model, which will still be very similar to the equidistant model. So once again, we have this ix and iy definition. And we will later also have this theta. But before that, we have, first of all, a const float, which is called x sq plus y sq, which is equal, let's keep this for later, which is equal to what is written here in this parentheses, in the square root function. It's basically x squared plus y squared. This is what this should mean. Then we have a const float, which is called square root of x squared and y squared. So we have the square root f of this definition x squared plus y squared. Okay, so this was simple. It's not really different to what was written there before. And then we have a whole range of constant floats. So we have the theta, which is 8 and 2 f of square root x squared and y squared and 1. Then we have theta 2, which is equal to theta times theta. Then we have theta, interestingly, 3, not 4, and 5, not 6, and 7, not 8. And we also have a theta 9. What is the difference? We have theta 2 is correct, theta 3 is theta 2 times theta. Then we have theta 5, which is theta 3 times theta 2, theta 7, which is equal to theta 5 times theta 2. And we have theta 9, which is equal to, let's keep this part for later, let's call it R. Theta 9 is equal to theta 7 times theta 2. And this R is calculated as theta plus K0 times theta 3 plus K1 times theta 5 plus K2 times theta 7 plus K3 times theta 9. Simple as that. Then we need to add a check if square root of x squared times or plus y squared is less than 1e minus 6. So if it's very small, close to 0, then we want to set the out x at position I equal to fx times ix plus cx. And similarly with out y, which is fy times iy plus cy. Else, you want almost the same code, but only almost. And we set it to out x at position I is equal to the same as before, but in front of fx and fy later, we'll write r over square root x squared y squared. And we'll also copy that in front of the fy term. And this will probably be it. Yes, we can delete the rest. So we simply check if the square root is close to 0 because we want to avoid it to be divided by we want to avoid anything being divided by 0, which would be the case here. And that's why we check that here. And this is our output value. Okay, lastly, we need to implement the Undistort pinhole constructor. So once again, I will copy that from the Undistort Canalabrant model. Undistort pinhole, creating pinhole undistorter. Read from file. Here we want to read 5 parameters. And the prefix should be pinhole. Okay, this is the constructor. Now we need the destructor. I will also copy that from the Canalabrant implementation and just rename that. And this is it. And now what about the distortion method, distort coordinates? For this I will copy the FOV implementation. So let's copy this whole method and let's put it here. Then we have this undistort pinhole, which still takes in an in x in y and will create an out x out y, and we have n number of points. This is a constant method. Then we do not have this distance and d2t, but we have the current camera parameters, which is fx, fy, cx, cy in this order. And we have OFX, OFY, OCX, OCY in this order again. And in this for loop, we start with I equals 0, I is less than n, and I++. We then store the x and y values. And we also create the ix and iy, which is the same as before. We can delete this r and fec variables. We want to calculate ix, which is equal to fx. We do not have this factor. Fx times ix plus cx, and fy times iy plus cy. And then we store this out x and out y using ix and iy. Okay, let me quickly check if we have all the constant floats here in this Canalabrant model. I think this should be fine. Okay, we are finished with the Undistort implementation, which at this point almost contains 1,500 lines of code. Of course, I have added quite a few comments, so it's the actual implementation is not that large, but still it took almost 4 + 2, 6 hours to implement it, in case that we know the original code base, just like in this case. But coding this up from scratch while having to think about what we want to do, this will probably take a much longer time. Okay. So now we have this header file and we have the Undistort.cc file, the implementation. Now let's try if it works. This will be the big question now. Let's double check if we have included the CC file in the CMakeLists file. Here, Undistort.cc, it is included. Let's save that again. Okay. Now I hope I did not forget anything. Let's try it out. Let's move to the Visual Slam directory and then into the LDSO Twitch. And let's open the terminal here. And now let's run make project. And let's hope for the best. Okay, it compiled without an error. I'm amazed with this many lines of code, but we are not using the new implementation yet. So let's see. We came from the dataset reader, but not the header file, but the actual implementation, which, as I now noticed, is the header file. So we do not have a separate file. And as you can see, there are many to-dos here, which we can now step by step get rid of. But let's start at the beginning. So here we have our include. We want to have that, so let's remove this to-do and let's save the file. Next, let's scroll through this dataset reader header. Up until here, everything is okay. Now we have in probably the constructor, yes, in the constructor of the image folder reader, we will create an undistort. Yes, we will create an undistort object. So let's get rid of this to-do. Let's save that. And we also want to get from the undistorter the original size and the final size of the images. Like this. So the identifier undistort is undefined. This is because it will probably be an attribute of this class, which is commented out yet. So we'll comment it in a second. In the destructor of the image folder reader, we want to delete the undistort object. And in this helper methods area, we want to have this get original calib, which should work. So let's comment this in. And this one should also work. Here in this get calib mono, we want to get the K matrix width and height. This is all stored in the undistorter. So we can comment out this part. To do empty in original code base, this is fine. get photometric gamma. This will check if the undistorter is 0. And if the photometric undistorter is also 0. So I think we can add a comment here. And it will return undistort, photometric undistorter get G. Okay, this should also be implemented. So we add a check if geometric and photometric undistorters are uninitialized. And here we have this attribute of the class or this field. We want to comment this in so that it is defined, and now all the errors should be gone. There are still some of them here, or not. Not sure. Something is going on here. And what is this? I think this is something I have added. I think this can be deleted. Let me still quickly check. For the get photometric gamma. Yes, this should be correct. Let us continue with the file. This to do can be deleted. And here we want to not create the null pointer. What do we want to do here? Load timestamps. uroc. Okay, minimal image B. Get image raw internal. This is something I have renamed. This was red2, which is kind of very generic. And this is equal to, this to do is equal to undistort with unsigned char. Then we have the mini or min img. And then we have not exposure, but exposures dot size. Here is exposures as well, timestamps. And we can get rid of this closing comment. And this should be okay now. Let's continue here. It's just loading the timestamps for the 3 possible data sets. Okay, that's it. Now we are actually using the photometric and geometric undistorters. So let's recompile and let's again hope for the best. And it still compiles. I cannot believe it. But will it run? Let's test it. Let's change directory into the parent. And let's run LDSO Twitch sequence. Okay. Now it has found the calibration. It has found the camera text file. But I have the feeling that it is stuck. It's not continuing. It's somehow not continuing. Let's see. Let's move to the main file. And let's see what is happening here. It is reading the calibration from the camera.txt file, it seems. Let us double check where the found is printed. Oh, here it is. So we have this get undistorted for file. Okay, this is being called. We are reading the calibration from the file. Reading calibration from file sequence 45 camera.txt. Okay, the file is good as well because we are printing this found. But we are not printing what kind of camera model we have found. So it's definitely stuck in this method. Okay. This means we need to debug that. Something seems to be wrong. So we have found the calibration file. Now it would be nice to see what is stored in this L1 variable. If it's really the line 1. Let's put it here standard, cout. L1 variable contains, and then we print L1. And we will see what this returns. So let's stop that and let's once again in LDSO Twitch, LDSO Twitch make project. Okay. It's using the relative path. So I need to change directory into LDSO Twitch and make project here. Okay, it has compiled correctly or successfully. And I can run LDSO Twitch sequence. Okay, so this L1 variable contains these values, and we can double check with the camera.txt file, and those values seem to be correct. Yes, they seem to be correct. Okay, so this works. So let's go further. And let's see, what do we need to, or what if a statement needs to evaluate to true? How many parameters are there? 1, 2, 3, 4, 5. So we need to check for 5 parameters. It should be this one. And this is L1 C string. Okay, let me quickly see out something here. Scanned 5 values. Now let's recompile. So sorry about that. I just need to find the bug. Or maybe it's not even a bug, I don't know. Okay, but it is not stepping into this part, weirdly. Okay. It's not evaluating this to true. Let me double check if I have made an error here. 395. Else if standard scanf L1 C string. Okay, I need to check what this returns. So this should return an integer. Now let's put it here. With a integer num_params is equal to this part. Oh, IC is not defined here. Num_params. Okay, let's recompile. and run. And it is not printing it. L1. Okay, there's something seriously wrong. Int num params. I hope this will not take a long time. But please bear with me. Let's turn on some music. Let's turn on the music or make the music louder while I think. So let's take a short break while I will try to find the error. Okay, I think I have found my typo. Not sure, but I think I I've written standard scanf, but it should be a standard sscanf. Which takes in the formatted string, whereas scanf okay, it's the standard input. Okay. This is why it is waiting for an input, and now it will continue. Okay, this explains stuff, of course. Okay, now what to do? We can get rid of this part, and now we need to change this scanf to sscanf at every occurrence. I am very sorry about this error. It's so easy to overlook. But it's also due to my minimum experience with C++, obviously, that I did not see that while coding. So this is Canada Brand. It's always scanf, it seems. scanf. scanf, scanf, scanf. And this should be every occurrence. Let's still search for scanf. There's always scanf. Okay. This should be corrected now. So let's try again. We need to compile it. And now we need to run it. Okay, now there's a lot happening here. Where did we stop, or where did we, what is new? So we have found, then we have scanned 5 values, found FOV camera model, building rectifier, creating FOV undistorter, input resolution is 1280 by 1024. Let's double check that. This is the input resolution. Those are the values rounded. Six, 695, 67, okay. Yeah, it should be correct. This is again the same value, fx, fy, cx, cy. Because this is in the range from 0 to 1, I'm assuming this is the relative calibration format, and we'll rescale this by image width over height to these values. They look a little bit more familiar to me. Out is rectify crop. Output resolution is 640 by 480. Finding crop optimal model. Initial range, iteration 1 to 5. With only minimal changes, it seems. And now the rectified camera matrix is this one. Now it's now the photometric undistorter is continuing with reading photometric calibration from file pcalib, reading the vignette, successfully read photometric calibration. This warning is here. Okay, now global calib is using pyramid levels 0 to 3. Causes resolution is 80 by 60. And then we have this exit. Let me see if I can simply add this in the main file. So init Google logging. Init Google logging. No, doesn't work. Okay, I have to look it up. To do at init Google logging. Whatever or however this is being done. But all in all, we can say we have finished the dataset reading, which is not a lot visually, but it is like for the functioning of the whole SLAM system, this is the important prerequisite. And yeah, we can be happy that we have finished that. It was quite a lot of work, many hours of work, but it is running, it is compiling, and it seems to be calculating important stuff for us, which we can hopefully use now. What I want to do now is I want to check the main file if we can comment in some of the next steps. So for example, the reverse play, we have the reader finished now. And we have this method get num images probably, so we can comment in this part. So this should still compile. And now let's recompile that quickly. And rerun. Okay, it's still working. Okay, now what is missing? The next part, or the next task we need to do is we need to implement this ORB vocabulary. And we need to load this vocabulary. And after that, we will create the full system, and the full system is really like the full system, so there's a lot of stuff going on here. I think this will take a long time, but then we will have the viewer. We will link the viewer with the full system here by setting the viewer and the full system. And once we have that, we should see a window popping up, which will probably only contain a user interface with some buttons and checkboxes. And then we will probably also be able to run through this thread. I think we can also use it. Yes, we have the reader. Let's do it. Let's do it here. So this to do can be removed. But why is this get timestamp not running? Image folder reader, get timestamp. Image folder reader. Image folder reader. And there's a get timestamp. Get timestamps. Get timestamps. And here we are using get timestamp. Okay, there should be, there's something wrong. So let me quickly look up if this is get timestamps or get timestamp. Get timestamp. Okay. Get timestamp. Okay. This should be get timestamp. But it is get timestamps. So let's change this. We are in the header file. So this should be okay now. Okay, next we can preload the images. I think we can also comment this in. Okay. Next we have the full system initialized. We do not have this yet. But we can preload the images using the reader. Okay. Now we have this important full system add active frame. But we also have an IMG. And this IMG is created here, so we need to delete that to clean up. So let's comment this in. This full system is not available yet. So we cannot use this at the moment. We do not have statistics. But we can we comment this in? I think we can. And we can also comment in this. So that we can hopefully get some statistics. What about this part? I think this can be used as well. We do not have the viewer yet. But this should... I think this should work. Let's see. If we compile again. Okay, it is stuck somewhere again. Or it will... or it needs maybe some time. Let us give it some time to finish. Okay. It seems to be working. So, ladies and gentlemen, this is our Visual Slam. We are finished. We are processing almost 3000 frames. We need about 7 milliseconds per frame. And it's finished. That's everything. So thank you very much for listening. No, of course we need to implement the main logic still, which is the full system, and the viewer is also very important for us so that we can see something on the screen. These are things that are missing, but before we can tackle that, we need this ORB vocabulary. Let me quickly look up how much work this will be. Where is this, by the way? ORB. Where is this ORB vocabulary implemented? Maybe we can use it already because it is in the library, the Debo 3 library, which is in the third party. Let's see if we take a look at the source. Vocabulary. Vocabulary.h. Vocabulary. And I think we have a type def somewhere. Maybe in the num types. Num types. Vocab. Okay. So the ORB vocabulary is of type Debo3 vocabulary. That means we should be able to use that. So let's try. And it is not throwing an error. So let's see. If we compile. Okay, it compiled and linked. Can run it. And it seems to... It is reading the dataset. We'll now see if it crashes or if it throws an error. We could of course also see what the voc provides us to check. Voc load. What does this load method return? One overload. Do we have some kind of indicator? Maybe a size? A score? Can check the size and the score. Is this a function call? Score. Oh, okay. It needs two vectors. Okay, we cannot use this at the moment, but the size is probably something we can use. So let's see out. ORB vocabulary has total size of, and then we add the voc size. And let's add, of course, an exclamation mark, because it's so nice. And let us see, so this runs. Let's make the project. And let's run it again. Okay, so ORB vocabulary has total size of this here. So we could basically check if the size is greater than 0. Maybe it would be interesting to see what the size is before the vocabulary is loaded. I'm sorry, I'm now a little bit more on the play side here. I want to try out different things, because now we have more to check and more to play with. So I'm trying to experiment a little bit. Okay, so in the beginning it has a total size of 0, and in the end it has a total size of whatever this size is. Let's see. Does it tell us the number of words in the vocabulary? Has let's say has words in the vocabulary. Okay, so let's check if voc. Let's maybe create an integer. Voc number of words is equal to voc size. So if voc number of words is greater than 0, we want to print how many words are there. I want to get rid of that. Okay, let's distinguish that. Okay. So let us check if this works. Has X word in the vocabulary. Okay, words. All right. This seems interesting. This is very interesting. Now, one thing I want to do in this part is I would like to set up the debugging pipeline at this point. Or do I want to do that? I think I want to. So in the VS Code, we have this bar at the bottom where we can simply compile the project, but we need to set the current build. And what I do here is I think I can simply use this one. And I want debug. Okay, let's also configure IntelliSense. I hope I did not destroy something. There's already an error here. This was not here before. Let's see. So we have the CMake here with the debug. What happens if I run it? Okay. It seems to be working. I think this path is hard-coded in the main file. This is this part. but there are no arguments passed here. So let's create a launch configuration. Okay, this is already working quite fine, but we can write a separate file for VS Code. We can create a new file, which is called launch.json. And in this launch.json, we can now add a configuration, it seems. For a launch, maybe like this one. Okay, so now we have different configurations here, and one of them is this GDB launch, and we can rename it to LDSO Twitch in debug mode. C++ debugger, launch, and the program, we have a template here, $workspace folder /bin/run LDSO Twitch tum mono. Run LDSO Twitch tum mono. Okay. Seems to be okay. Then we have arguments. This is important. So this is important because here we need to pass in the arguments that are parsed in the main function. Stop at entry. This can be true. Okay, the setup commands are fine. Okay. I think we are almost good to go. Let's see, where is this? Okay, let's try to add some arguments. Like, for example, we want to have the preset equals 0. We also want to have the files is equal to the parent directory twice. So we go from the bin directory to the workspace folder and then one up. Then there's a vslam datasets folder. Then we have sequence 45 and then images.zip. And we also have this similar with the calibration files. So let's double check the file path. vslam datasets, sequence 45, images.zip. Next we will have not files but vignette, which is called the vignette.png. Next we have the calip. Calip, which is the camera.txt. Next we have the vocab, which is contained in the current folder. Probably the parent folder. And then we have vocab. And in vocab we have the file ORBVocabulary. Then we have the gamma argument, which is in the vslam dataset, sequence 45, and is called pcalip.txt. Okay, now if I did not make a mistake, can play the play button here, and it's not working. I think I need to set this configuration somewhere. Not here, not here. I think I need to look it up, or do I need to save it? Of course. Fresh Explorer. Maybe I need to reopen that. Let's close this and reopen it. Let's configure it. So it seems that CMake is compiling it with the build type string debug. So this seems to work for the debug build. But if I play it, it's not working. If I start the debugger, okay, so it's calling the Undistorter get original size, but it probably does not have the correct arguments passed. But let's check this. When I set a breakpoint, so here in the main function, I want to set a breakpoint in the beginning. And let's now rerun that. Okay, and it is actually stopping in the main function. Let's continue. And let's see, argc, it has 7 arguments. And the arg values, let's see if we can load them. it is 47. Okay. Why the heck is it 47? That's step 1 below. It does have 7 arguments, which is interesting. Preset equals 0. This looks good. So it is loading a preset 0, but this could be a coincidence. But it has also the file, so maybe it's running now. Let's play. Error, reading archive. Images.zip. Why is there an error reading the archive? Let's maybe remove this breakpoint and rerun it. So it stops at the beginning of the main function, which is okay. This is something I have defined in the launch JSON with stop at entry equals true. So this is perfectly fine, and then if it runs, it will have an error while reading the archive. Okay. It's halfway working. I will fix that at some point. Okay. So I would say this is it for this part. The video is long enough, about 3 hours almost. Yeah, I hope you had some fun watching it or maybe trying it yourself. I will now take the current state of this code and upload it to GitHub. You will see the link in the Twitch page and in the YouTube page if you want to code along. As always, if you have any questions or comments or helpful critique for me, feel free to write it, to post it, to just get it out there so that I can read it. And with these words, I thank you very much for watching and have a great evening, night, morning, whatever it is on your side, and see you next time. Goodbye.